Hello everyone, welcome to the next section of the course, Discovering Hidden Structures with Unsupervised Learning. In unsupervised learning, the learning is shown only in the input data and is asked to extract knowledge from this data without further instruction. Now we move on to the first video of this section that deals with understanding unsupervised learning and k-means clustering. So, unsupervised learning might come in many shapes and forms, but the goal is always to convert original data into a richer, more meaningful representation, whether that means making it easier for humans to understand or easier for machine learning algorithms to parse. Let's look at some of the common applications of unsupervised learning. The first application is dimensionality reduction. This takes a high-dimensional representation of data consisting of many features and tries to compress the data. Next is factor analysis. This tries to find the hidden causes or unobserved components that give rise to the observed data. And the last application is cluster analysis. This tries to partition the data into distinct groups of similar items. Next, we move on to k-means clustering. The most essential clustering algorithm that OpenCV provides is k-means clustering, which searches for a predetermined number of k-clusters, or groups, within an unlabeled multidimensional dataset. It's easier to understand the algorithm by looking at a concrete example. Now we'll implement our first k-means example. First, let's generate a 2D dataset containing 4 distinct blobs. To emphasize that this is an unsupervised approach, we'll leave the labels out of the visualization. Adding these 3 lines of code, we'll continue using matplotlib for all our visualization purposes. Recalling the same steps from previous sections, here we'll create a total of 300 blobs belonging to 4 distinct clusters. On executing the code, this output will be generated. Example dataset of 300 unlabeled points organized into 4 distinct clusters. You can see here that even without assigning target labels to the data, it's straightforward to pick out the 4 clusters by eye. The k-means algorithm can do this too without having any information about target labels or underlying data distributions. Although k-means is a statistical model, in OpenCV it does not come via the ML module and the common train and predict API calls. Instead, it's directly available as cv2.kmeans. In order to use the model, we have to specify some arguments, such as the termination criteria and some initialization flags. Here we tell the algorithm to determine whether the error is smaller than 1.0, or when 10 iterations have been executed. Let's execute it. Then we'll pass the preceding data matrix, x, to cv2.kmeans. Also, we specify the number of clusters as 4, and the number of attempts the algorithm should make with different random initial guesses as 10. That's shown in the highlighted part of the code. 3 different variables are returned. However, we'll only check for the compactness score. It returns the sum of squared distances from each point to their corresponding cluster centers. This number strongly depends on the actual values in X. A high compactness score indicates that all the points are close to their cluster centers, whereas a low compactness score indicates that the different clusters might not be well separated. Hence, it's more informative to plot the data points, coloured to their assigned cluster labels. For that, we'll implement this code snippet. This produces a scatter plot of all the data points, coloured according to whichever cluster they belong to, with the corresponding cluster centres indicated with the blob of darker shade in the centre of every cluster. So, this is the result of the k-means clustering for k equals to 4. The good news here is that the k-means algorithm, at least in this simple case, assigns the points to clusters very similarly to how we might have had we done the job by eye. But how did the algorithm find these different clusters so quickly? Fortunately, an exhaustive search is not necessary. Instead, the typical approach that k-means takes is to use an iterative algorithm, known as expectation maximization, which we'll see in the next video.